Hello everyone, this is the number theory tutorial. First of all, we would like to find the last digit of 7 power 100. 7 power 100 is a very large number. You can't even put it on your calculator and find the last digit. However, in order to find the last digit of any number, we can take that number, which is 7 to the power of 100, and take it mod 10. Okay. So again, 7 to the power of 100 is a large number, so we need to simplify it. This could be 7 to the power of 2 to the power of 50. Okay. 7 to the power of 2 is 49 power 50 mod 10. And then we can use the congruency property. So 49 mod 10 is 9. 49 contains 4 tens. The remainder would be 9. Or negative 1, which is 9 minus 10. And then we take the smallest number regardless of the sign, so it doesn't matter whether it is positive or negative. We are trying to simplify it, so 1 is the smallest number here, so you can substitute negative 1 instead of 49 because both of them are congruent. So negative 1 power 50 mod 10, so negative 1 power 50 is 1 mod 10. 1 mod 10 is finally 1. This means that the last digit of 7 power 100 was 1. Then in year n, the 300th day of the year is a Tuesday. In year n plus 1, the next year, the 200th day is also a Tuesday. On what day of the week did the 100th day of the year n minus 1 occur? So the year before that. So first of all, between the 2 Tuesdays, we had a full week, meaning that we had from Tuesday to the next Tuesday 7 days, and then to the Tuesday after that, and so on. So the number of days between the 2 Tuesdays at year n and n plus 1 can be either year n was 365 days. So from 300 to 365, there are 65 days remaining, and then there is the 200 days from the year after that, which is year n plus 1. So between the 2 Tuesdays that we have, there exists 265 days. Or year n could be a leap year, meaning that it contains 366 days. So from the day 300 till the end of the year, we have 66 days left, and then we have the 200 days of year n plus 1 till we arrive at the other Tuesday. So we have in total 266 days. So which one is the correct one? Is it 265 or 266? So in order to get both Tuesdays, this means that the week ended and there are no remaining days. So if we take mod 7 for both of them, 265 mod 7 is 6, 266 mod 7 is 0. This means that year n was a leap year. This also means that the year n minus 1 was not a leap year. Okay. So now let's calculate how many days are there between the question mark, here the day that we are trying to find in year n minus 1, and a Tuesday in year n. So now we know that n minus 1 is not leap, so it must contain 365 days only. So from day 100 till the end of the day, there exists 265 days left, and then there are 300 days in the year after that, which is year n. So between the question mark, the day that we are trying to find, and the Tuesday of year n, there exists 265 plus 300, which is 565 days. So again, to get the day itself, we take that number, 565 modulus 7, and we get 5. This means that from Tuesday in year n, the 300th day of year n, we keep going back till the Tuesday after that, and one more Tuesday, and so on, till we are left with 5 days, 5 remaining days. This means that from Tuesday we can count back 5 days. So we have Monday, Sunday, Saturday, Friday, and Thursday. The question mark here is Thursday. The next question. Which digits must we substitute for A and B in this number so that the resulting integer is divisible by 13? So for any number to be divisible by 13, this means that this number mod 13 equals 0. And again, 30, A0, B0, 3 is a very large number, so we need to decompose it. So this takes us to 3 million plus A times 10,000, B times 100 plus 3. All of that mod 3 equals 0. And in order to write that in a formal way, you can write it as 3 times 10 to the power of 6, A times 10 to the power of 4, B times 10 to the power of 2 plus 3. And again, all this mod 3 equals 0. So now we can use the congruency and try to find a congruent for 10 mod 13. So 10 mod 13 is 10 or 10 minus 13, which is negative 3. And the smallest number here is negative 3. This means that in order to simplify this equation, we can substitute negative 3 instead of 10. So we can remove all 10s and add negative 3 instead. So we end up with this equation. And again, negative 3 power 6. 6 is an even power, so we can eliminate the negative. Again, negative 3 power 4, we can remove the negative sign and so on. So this takes us to the next equation. And again, we can use congruency to split the 3 power 6. This 3 power 6 can be written as 3 power 3 power 2. Why did we do this? Because 3 power 3, which is 27, mod 13 is 1. 27 contains 2 13s, which are 26, and the remainder is 1. So again, we can remove 3 power 3 and substitute with 1 instead. Just take this to this equation. So we end up with 3 plus 3a plus 9b plus 3 mod 13 equals 0. And if we sum both 3's, we get 3 plus 3a plus 9b mod 13 is 0. This means that the entire equation here, 6 plus all of this mod 13 equals 0. Meaning that all this, the entire bracket here should be a multiple of 13. So if we have a 6, 3a plus 9b should be a 7. Actually can be a 7 or 7 plus 13 or 7 plus 13 plus 13. So all of them are congruent. So 3a plus 9b is congruent to 7 or 7 plus 13, which is 20, or 7 plus 13 plus 13, which is 33 mod 15, and so on. So to simplify things, we can take the 33, since 3a, 9b, and 33, all of them can be divided by 3, and 3 and 13 are relatively prime, so they don't share any common factor. So if we divide all of them by 3, we get a plus 3b equals 11 mod 13. And remember that a and b are digits in the original number, so these must be integers. We can't have, for example, a 1.2 or something of this kind. Okay. So now a plus 3b are single digits, and their summation should equal 11. This means that we either have a equals 2, b equals 13, which leads to 11, or a equals 5 plus 3 times 2, which is again 11, or 8 plus 3 times 1, which is 11. In the next question, we have using Fermat theorem, find 3 power 201 mod 11. So remember that Fermat states there that a power p minus 1 equals 1 mod p, where p should be a prime number and a is a positive integer, and a and p are relatively prime, meaning that a and p don't share any common factor. So in order to get the same format at 3 power 201 mod 11, this means that the p, the number after the mod, should be 11, and the base, which is the a, should be 3. And by substituting with 11 and 3 in Fermat theorem, we get 3 power 11 minus 1, which is 10, equals 1 mod 11. So from this one, we need to reach 3 power 201. So we can add power 20 to both sides. So we get 3 power 10 power 20. And in the right hand side, we get 1 power 20, which is 1. We can also multiply by 3, since a equals 3, in order to get the 3 power 201. And on the right hand side, we get 1 times 3. So we end up having 3 power 201 equals 3 mod 11, which is 3. So finally, notice in the table below values of Euler-Touchen's function phi n, that phi n is even for n greater than 2. This is true for all n greater than 2. Give a concise argument why this is so. So for n equals 1 and n equals 2, phi n, the Euler-Touchen of n, is 1. So these are the base cases. And then for any n greater than 2, so from 3, 4, 5 and all the numbers, we have phi n equals 2, 2, 2, 4, 2, 6 and so on. All of them are even numbers. So remember, in these tutorials we proved that phi of p, the Euler-Touchen of any prime number, is p minus 1. We also proved that phi of p power I, the Euler-Touchen of any prime number power I, is p power I minus p power I minus 1. We also know that according to the fundamental theorem of arithmetic, that any number n can be factorized into prime numbers. So now, if we take these prime factorization, all prime numbers, which are 2, 3, 5, 7, 11, 13 and so on, the only even number is 2. Other than that, so starting from 3, 5, 7 and so on, all of the rest of the prime numbers are odd numbers, which makes sense. If we have any even number after that, it would be a multiple of 2, and thus it won't be a prime number. So if this is an odd number, which is the case with all prime numbers except for 2, so a prime number, phi of any prime number, would be p minus 1. So it would be an odd minus 1, which is an even number. So prime factorization of any number would lead to an even Euler-Touchen. But what if the prime factorization contains a 2? So if this is the case, the prime factorization would be 2 to the power of some number k. And 2 to the power of k, given this theorem, leads to 2 to the power of k minus 2 to the power of k minus 1. And if we take 2 power k as a common factor, that by 2 power k times 1 minus half, which is 2 power k times half, which is 2 power k minus 1. So again, 2 power anything is also an even number. So whether the prime number was odd, which is the case of all prime numbers, or the prime number was a 2, in both cases this will lead to an even Euler-Touchen. Thank you.